Hello, physics kids. We are going to continue working in chapter 20 today. And I kind of mentioned this a little bit yesterday when we were talking about um, how when waves interact with each other, we can get constructive interference or destructive interference. And when we get constructive interference and things are in phase, then we get what we call resonance. Okay, so let's start with that resonance. Wow, sorry. I'll do better, I promise. Okay, um, so resonance is, and I hope the name kind of, something you kind of recognize. Um, Resonance is not just when waves interfere and constructively interfere, but when we can make something match the natural vibration or the natural frequency of the object, we're going to get resonance. Okay, resonance, the word itself means to resound, right? Almost like an echo, but it's more complicated than that. Okay, um, and again, we need something that is elastic, all right, to be able to resonate, right? It's got to be able to vibrate on the same frequency as the object that is causing the vibration. Okay, I mean, if you think about resonance, one of the easiest ways to kind of think of resonance is you think about when you're a little kid and you would sit on the swing set, right? You have to get your legs to go in the correct direction at the correct time, or you don't increase your swing, right? Or you don't even maintain your swing, and it actually works against you. So when you're moving forward and you're getting ready, you got to get ready and swing your legs back to go backwards. And then as just before you get to the very back, you got to swing your legs forward to get it to go forward. So that's kind of an example, the easiest example of resonance. Okay. Um, and as we continue to match the resonance in a swing, the quote unquote amplitude is going to get bigger, right? We can swing farther and farther and farther and farther. All right. So let's take a look at the example with a tuning fork, right? What's kind of cool, and again, we don't have this demonstration. I'll try to get that to you if I go to my classroom. But if we took a tuning fork and we struck it, and we put it close to another tuning fork that had the same natural frequency, it would actually cause the second tuning fork to vibrate, and they actually would then constructively interfere, and we get a bigger amplitude than just a single tuning fork that was struck. Even though I didn't strike the second tuning fork, it would start to vibrate and resonate with the first tuning fork. Okay. Um, and so that's probably the easiest way to create some resonance. Okay. Um, if the tuning forks do not have matching frequencies, then resonance will not occur because the frequencies can't match up. Okay. So that's something to keep in mind. Resonance occurs, whenever you have pulses applied to a vibrating object if it's in rhythm with its natural frequency. If it's not, then you have some problems. So this is kind of crazy, but in 1831, cavalry troops that were marching across a bridge in Manchester, England, caused the bridge to collapse because they were marching at such a good rhythm that it created resonance and it amplified the vibrations of their feet as they were marching, and it actually caused the bridge to collapse. So ever since then, both the English army and the American army, the British army and the American army, whenever they cross a bridge, they would break step. Meaning just walk at whatever you want, because as long as you have some people not in step, it's not gonna cause as much resonance because you're gonna get some destructive interference. Okay. However, there has been another um, natural disaster caused on a bridge because of wind, and I'm going to send you a video of that. It actually happened in 1940. There's this new bridge in Tacoma, Washington. It was only 4 months completed, but because of the winds, it started kind of rocking and rolling and twisting, and it just so happened that the rhythm of the wind blowing it happened to match its natural frequency. And guess what? It amplified it. And that bridge ended up collapsing, but it resonated and it rocked and rolled for quite a long time, quite a few hours. There were actually people on the bridge when it started, but they were able to walk off because it didn't collapse right away. So anyway, they had to start then thinking when they constructed bridges, we got to know, we got to make sure that the wind can't match its natural frequency and thus create resonance and amplify its waves, so to speak. Okay. Um, Resonance happens in other ways as well. We might see resonance in, obviously, in the sound of music. I don't know if you've ever experienced this phenomenon, those of you who are singers, but let's say that you are, that there's somebody on stage singing and you're out in the audience singing, right? And if you happen to match pitch perfectly, you hear a resonance, right? Meaning there's a sudden amplitude, right? You could have this with guitars, violins, any type of musical instrument. When that pitch is exactly on, right, we get this sudden resonance, this sudden amplification of volume, and that happens when we get those things. You also see sometimes with the height of ocean tides, we get some resonance. Lasers have resonance. Anyway, there's a lot of different ways that nature deals with resonance. Okay, now that happens, as I said, when the wave patterns are in phase, right? They're exactly the same. Their crests match up, their troughs match up, right? Or their compressions match up exactly, and their refractions match up exactly. Okay. Now, we could also look at the other side of that and look at interference. And as I mentioned to you earlier, you could take two speakers and um, face them towards each other and attempt to try to cancel out the sound. You could even do that if you were just to switch the positive and negative wire inputs to one of the speakers, so they're exactly out of phase. You could do that as again. Um, that's one way that speakers work. Two speakers work is that they should be in phase, right? So it amplifies the volume. But if they're out of phase, it could actually lower the volume because you're gonna get some destructive interference. Okay. All right. Um, let's talk a little bit more about interference. Okay, so as we talked about in chapter 19, if we have the crests or the compressions of one wave matching up exactly with the other. So here's kind of a cool thing. Let's say that you were sitting in a chair. Why is my pen not working? Okay, let's try that again. All right, let's say that you kind of set up so that you're in a chair right here. You're sitting in this chair, and you have a speaker here, and you have a speaker here. And if those speakers are the same distance apart, right? When the waves, let's say these are the compressions, right? If these compressions are perfectly matched up, as I just drew them to not be. Um, Let's try this again. Okay. If I can get that to work. Um, let's go the other way around. Right. So let's say that these match up perfectly, then the sound is actually going to be amplified. Right. But if you were to move your chair a little this way or a little this way, there's going to be some canceling out. Right. So why do you just, what you would think, well, we just wouldn't hear anything. Well, a couple of things to keep in mind. Right. There's reflective surfaces. If you're in a room, if you're in a theater, there's more than one frequency coming at you, and some of those frequencies might cancel out, but others of them might not. Okay. Plus, you're going to get a lot of reflection off these walls, hopefully, and those reflected waves might fill in wherever the destructive interference happened. So most of the time, you don't get any quote unquote dead spots, but there are theaters and concert halls that are a little older where they did not take these things into consideration, and there are actual dead spots where you cannot hear in a theater or auditorium very well. So kind of a not a very good thing. Now, the cool thing is this is actually something that is useful that you guys probably use all the time if you've ever used noise canceling headwear, right? So um, how do I want to say this? So like when construction workers have to use heavy machinery that makes a lot of noise, they might their company or the company that makes like a jackhammer or something has started to equip the jackhammers with headphones and microphones that send the sound of the jackhammer back into the speaker and thus causing it to cancel, right? And actually, if you have the only way you can have noise canceling headphones is if they're powered, okay? Because that's exactly what noise canceling headphones do is they detect the sound wave that's coming in, and they send an identical sound wave out, so that out of phase, completely out of phase, so that one caress or one compression matches up with the refraction, and they completely cancel each other out. That's how noise canceling headphones work. Okay, but it has to be powered, because it can't just you can't just have thick headphones and say they're noise canceling. They might be noise inhibiting, but they are going to cancel unless they are sending out a signal for themselves. Okay. Um, all right. Going to. Okay, we're going to talk next about beats. Okay. It's kind of a tough topic, except I want you to think of um, greatest common factors when we think about beats, believe it or not. Okay. So, for example, the way this works, it's not really the way you think. It's not like a tune or a rhythm necessarily, but they call these beats when you have two objects that are giving a different frequency. There's still going to be times, if they're depending on how they're phased, where the compressions of one and the compressions of the other do match up sometimes, right? So let me give you an example. If this is sound source 1 and this is sound source 2, okay? I'll use a different color here. And so I'm gonna kind of do this a little differently. Maybe. So let's say that each one of these lines that I'm drawing is a compression, okay? And for this one, each one of these lines is a compression. Now imagine that they are spaced evenly out and everything, okay? I know they're not quite, but I tried. If you notice then that this section right here, those two compressions happen to match up, okay? Even though there's nothing with this one, but this would be called a beat, right? Because if those compressions match up at just that point, we're going to get an amplitude increase, right? It's going to get louder for just that moment because we're going to get some resonance off of that. Okay, and so the music might be going, then all of a sudden you get this loud part. Well, that just happens to be where two compressions matched up, and what in science, in the world of sound, we call that a beat, right? And so this would be a beat, and this would be a beat, and this would be a beat. And anywhere two compressions of different frequencies, right? I hope you can see that these two are different frequencies from each other, but they can still have beats because they can still have compressions that line up. Now, the crazy thing is that these points where they don't line up, right? Like right here, they don't line up. And so we're actually going to get a little bit of destructive interference right there, because some of this compression is going to match up with some of this refraction that's right here, and they're going to actually cancel. So that's why we kind of get these different amplitudes with two different sound sources. Okay, so we want to make sure that if we're trying to create a nice sound, that we try to match those things up. Okay, so a beat is a periodic change in the loudness of sound. Okay. All right, let's use another example of somebody, a father and daughter walking in step, right? So, like the dad's stride might have this type of frequency, right? But the daughter's stride, oh, we'll make it pink for the little girl, right? Might look like this, right? But there's times when the steps are going to be in sync, and there's going to be other times they're not. If you ever try to walk with somebody and your steps are not in sync, it does feel a little bit like destructive interference. Okay, but there would be times in this scenario where we'd get some steps that were in sync, even these ones, even though they're opposite foot. They're hitting the ground at the same time. Okay, so that'd be another place where we'd have a beat at these spots here, and everywhere else we'd have destructive interference. Okay, and so that's why I kind of said this has to do with like greatest common factor. Okay, I don't know if you've ever done that problem where they talk about like every third locker has this scenario, and every sixth or every fifth locker has this scenario. How many of them will have the same scenario? Well, I guess it's probably more like least common multiple now that I mention it. You know, every 15th locker, right, is going to have those two things the same. And we're kind of doing the same thing with these beats. Okay. All right. So let's do an actual example with some steps. And let's use a small rabbit and a tall rabbit. Okay. So let's say that, just so we can kind of see if we can figure out the math of it. Let's say a tall rabbit, okay, goes 70 hops per minute. Okay. And the shorter rabbit can go 72 hops, has to go 72 hops in a minute. Whoa, that's supposed to be an S. Okay. So obviously the shorter rabbit has to hop faster than the taller rabbit. Okay. So how would we figure out how many hops before they are the same? Okay. So let's see if we can kind of figure that out. Now, it'd probably be easier to break this down into seconds, right? And so we could say if we go 70 hops in 60 seconds, right, and 72 hops in 60 seconds, how many hops per second is that? We could say that's 1 and 1/6 hops per second, right? Is that right? 7/6. And then for this other guy here, if we divide each of these by 12, right, we get 6/5, which is 1 and 1/5. So actually, I'm going to leave that. And so this is 7/6. So when will these be? When will these make a step at the same time? Okay. Well, look at the denominators, right? The common denominator would be 30, right? Now, obviously this one will have gone 36 hops in those 30 seconds, and this guy would have only gone 35 hops in 30 seconds, but that's going to be the first time that they land at the same time, right? So here's the real question is how many times will they be in sync throughout 1 minute? Well, they start off, it's in sync, and then it's not until 30 seconds that we see them being in sync again. And then again, obviously another 30 seconds. So within a minute, they're only going to be in sync twice during that time. Okay. So let me go back and just talk about that real quick here. So all I did was, oops, I already did that. All I did is made a fraction and reduced it. Okay. And then got a common denominator between these two things. Okay. In order to figure that out. All right. So now let's see if we can apply this to a tuning fork. Okay. So if fork one vibrates at um, 264 hertz and fork two vibrates at 262 hertz, right? Um, they are going to be in sync 2 times per second. Okay. 2 times per second. And this is the way that we figured that out. So go back to the bunny hopping thing where we had 70 and 72. We said that there'd be 2 times per minute because that was their rates, that they would be in sync. And the way we do that is we just subtract these. Okay. And so the same thing here. Just subtract those to find out how many times per second we will get a beat. So we'll get a beat. We call this a beat frequency of 2 hertz. Sorry, trying to do two things at once here. Okay. Okay. All right. Okay. We'll talk more about this beats thing when we work on some of the homework problems, but just keep in mind that beats can actually help us because sometimes, like if you're tuning an instrument, you're using a guitar and a piano, and you play them both at the same time, you might hear some beats if one of them is out of tune a little bit, and so you keep tuning it until you have no beats, right? Because no beats means that they are perfectly in sync with each other. They're perfectly in phase. Same thing that again we talked about, like dolphins use this to detect movement and stuff like that, along with the Doppler effect. Because think about the Doppler effect, you're getting you're getting a bunch. The frequencies are starting to bunch up, right? And so you could use that as an echo as it's coming back. There's going to be some beats when those frequencies match up perfectly. Those compressions match up perfectly, and you're going to get this kind of louder sound if you're a dolphin, and you're going to know something is moving towards you or moving away from you. Okay. They actually use this to detect dangerous gases in mines because there's a slight difference in the speed of sound in methane versus just regular air. Okay. And so they send some. Um, how do they do that? They send air through two different pipes. One is pure air, and one is air from the mine. Okay. If there's no beats, then they know that the air in the mine is pure because it matches with the air that they're synthetically pumping through a pipe, right, of pure air. If there's beats, though, they know that the speed of sound in the air from the mine is a little bit different, and so the beats are there, and they know that there's methane gas in the mine, and they can't go down there. So, just another little application of beats. All right, so that is it for this chapter. I'm hoping by next week we can be using Zoom because I didn't like this. Anyway, thanks, and make sure you write down any questions that you have, and we'll go from there.